Hello, in this video I'm going to be talking about resonance and resonance structures for molecules. So ultimately by now you should be pretty comfortable with drawing Lewis structures, and you should be pretty comfortable with the difference between a single bonded oxygen with a negative charge and a double bonded oxygen that has a formal charge of 0. Because ultimately resonance is going to involve a lot of oxygen bonding, particularly double bonding and single bonding. So if you're not comfortable with the typical bonding patterns of oxygen, I would go through and refresh that a little bit, because you'll need to have that under review before you head into thinking about resonance. So what is resonance? Well, resonance really, if you want to get technical, is called a delocalization of electrons. So we normally like to think of electrons as highly mobile, and typically if electrons are going to find a new place to go, they're going to go to that new place. So when you have a wide array of spots where electrons can move to, they're going to start moving around into those various spots. I like to think of it kind of like musical chairs or like a merry-go-round. So in musical chairs, you get up and you move around until you find a new spot to go to. That's kind of like electrons with resonance structures. They're finding those open slots that they can go to, and they're going to them. And so you want to think of them alternating between being in a lone pair and a bond. So if you have a lone pair, if there's an opportunity for that lone pair to become a new bond, it's going to take it, and so on and so forth. But new bonds aren't created or destroyed, they're simply relocated. So if we form a new double bond in a molecule, then an existing double bond has to go and become a lone pair, and we'll see that in a minute. So it's like a take and it's a give. We take away a double bond, but we put a new double bond in its place. So just electrons constantly moving around. And like I said, most commonly we're going to see this going on with oxygen. And we represent it with arrow notation. So I know I keep saying this a lot, but if you go on to take organic chemistry, arrow notation is vital. Arrow notation is basically the language of organic chemistry, because a lot of organic chemistry mechanisms are built on the concept of moving electrons around. And arrow notation is how we show electrons being moved around. So let's look at an example of resonance in action, because I think resonance is a lot easier to show than it is to explain. So let's take the sulfate ion, SO42-. And here we've got a valid Lewis structure for SO42-, where we have the two double bonded oxygens on the sulfur, which both have a formal charge of 0, and we have two single bonded oxygens, a formal charge of -1 each. So this oxygen has a -1 charge, this oxygen has a -1 charge. So ultimately, if we wanted to demonstrate resonance taking place on this structure, first I want to look at this oxygen here. And I'm just going to pick a lone pair on this oxygen. We have 3 lone pairs to choose from. I'm going to choose this one. And I'm going to draw an arrow to this bond here. And what this is showing is the formation of a new double bond. So we're taking these electrons here and we're putting them into a new bond here, turning this single bond into a double bond. We're not pulling electrons from just anywhere, we're pulling them from the lone pair on this oxygen and making a new bond with it. But like I said, for every new give, there's a take. So to give this new double bond to this oxygen, we have to go to another oxygen, one of these two down here, and we have to take away one of these double bonds. It doesn't really matter which one we do, but I'm going to take away this one. And what I'm going to do is I'm going to draw an arrow pointing to this oxygen. And what this does is it shows this double bond right here relocating as a lone pair on this oxygen. So we're taking this lone pair on this oxygen and making a new double bond with it, and we're taking this existing double bond and making a lone pair with it. And that's the basis of resonance. You're basically just moving electrons around. So let's look at what that would look like after the fact, after we've moved those electrons around. So this would be the result of those electrons moving around. This red line here is that new double bond that we formed, and these two red lone electrons are the bond that we moved to the oxygen as a lone pair. And you'll notice that this new structure isn't fundamentally different to the structure we started with. All we did was move some electrons around. That's the name of the game with resonance structures. These two would be resonance structures of each other. Resonance structures have identical properties, just different locations. So the fundamental properties of the molecule are the same, where we have two double bonds and two single bonds, but the location of those bonds has changed. And you can do this any number of times. You can do this an infinite number of times. You can just keep moving electrons around. You know, you can take a lone pair from this oxygen and move it to right here, and you can take this double bond and move it to this oxygen, and you can do that so on and so forth until you're just moving these double bonds around the sulfur constantly. So essentially electrons are just constantly moving between bonding and lone pairs, bonding and lone pairs, bonding and lone pairs. And it's just going to move around like a carousel to the point where those electrons are constantly delocalized, which means they're never in one place for any 1 second. So at any moment in time, one of these oxygens is going to be double bonded, and it's also going to be single bonded. So it really doesn't matter which oxygens you show as having the double bonds or having the single bonds, because at any moment in time, they're doing either one. They're either single bonded or double bonded at any given moment. And there's actually a special way that we can show that, where we can show that the resonance is constantly shifting between all four of these oxygens. So this special structure here is going to be known as the hybrid structure, or the resonance hybrid structure. And what these red dotted lines are showing is that those two double bonds of this molecule can be on any of these oxygens. Those double bonds are just constantly moving around. So if you want to show that as a hybrid structure, this is how you would show it, where this is showing you all the potential hybrids, all the potential resonance structures rather, at once, versus showing each individual resonance structure. You can just say, hey, they all have the potential to do it, so I'm just going to show you that they all have the potential to have that double bond on them at any given time, because those electrons are just constantly moving around. So let's look at an example really quick that's different from what we just looked at. So this is going to be called the acetate ion, and this is the ion produced from the dissociation of acetic acid. So once the hydrogen breaks off from acetic acid, we're left with this, which is the acetate ion. And so you'll see here on this second carbon here, we've got two oxygens bonded to it. We have a single bonded negative oxygen, and we have a double bonded neutral oxygen. And so using your resonance skill that we just saw with the sulfate ion, how do you think the electrons are going to move here to move this double bond to this oxygen instead of it being on this oxygen up here? So we know the double bond is going to move down here, but how exactly is that double bond going to form, and how is this double bond on this oxygen going to be taken away? Take a few seconds, pause the video, try that on your own, and then unpause it and see if your assumptions and your work was correct when you see what I've done for it. So here you go. Here's the formation of your resonance structure. So ultimately what you're going to do is you're going to look at this negatively charged oxygen, just take one of its lone pairs and move it to make the double bond here. And for this oxygen up here, you want to make sure you take the double bond and make it a lone pair on the oxygen. And the main reason you have to do it like this is that if you don't do it like this, then you would end up with more than 4 bonds around the carbon. And we know that carbon absolutely cannot have more than 4 bonds around it. So you definitely want to show both of these things happening at the same time. And this is a skill you learn a lot in organic chemistry, because in organic chemistry you're just constantly moving electrons around. And so this is our new structure, where we have a double bond on this oxygen now and a single bond on this oxygen. Both of these structures are valid, and that's sort of the takeaway for resonance structures. For resonance structures, they're simply multiple valid Lewis structures for the same molecule, because all you're doing is moving around where the electrons are located. Both of these structures would be valid, so because both of them exist at different points in time. So if you wanted to draw the resonance hybrid, you would just draw your dotted line on both of these oxygens connected to the carbon, where we're showing that at any given time the double bond is on both oxygens. It alternates between the two because those electrons are constantly mobile. So to kind of wrap things up with resonance, essentially with resonance you're just moving electrons around. You're moving them from being bonds to being lone pairs to being lone pairs to being bonds. You most commonly see it with oxygen, and just remember that electrons are being relocated, not created or destroyed. So you can't just pull some electrons out of nowhere and create a double bond. They have to come from a lone pair on the atom that you're creating the double bond to. So there is the idea of resonance, and hopefully this helps clear up what's going on when you're going to draw and identify your proper valid resonance structures and or your resonance hybrids.